Okay, guys are back. Elias, Samal. Okay, نكتل. Okay, አይሰማም ሚውት ስላደረጋችሁት። ስለዚህ I'm hoping everything is okay now, so I'll just continue. I just started recording it again, so hopefully the recording will be there. Okay, cool. So, as I was saying, when we define minerals, they should be naturally occurring, they should be solids, they should be inorganic, they should be made from ordered arrangement of atoms. Therefore, we know what they're composed of, so we can predict their composition. So based on all these facts, then we can, for example, use that and try to extract some value from them. Because when we say chalcopyrite, as I said, we know it has copper in it, iron in it, and sulfur in it, and the copper part is a valuable one. So we can use that as a method, as a source for extracting copper from it. So generally speaking, when we dig something from the ground for its economic purposes, that is to extract the valuable commodities like gold, copper, and so on. As I said last week, the vast majority of what we dig from the ground is waste. So in this case, maybe more than 90% of whatever you dig from the ground is composed of silicates and carbonates. And these are the ones that we refer to as gang minerals, because typically we don't get any value from these silicate and carbonates. So I'm talking in general here. So these are called rock forming minerals. Most silicates and carbonates, we call them rock forming minerals. The ores, which we normally extract value from, are, for example, native elements such as gold, silver, and platinum, or sulfides, which are good sources for lead, copper, zinc, and so on, and oxides. Oxides are very good sources for iron and a number of other ferrous metals like titanium, manganese, chromium, and so on. Okay. So obviously, this doesn't include everything. For example, if someone is interested in lithium, which is one of the critical elements at the moment, lithium usually tends to occur either in brines, which are saline water bodies, or lithium can be found in silicates. For example, spodumene, petalite, lepidolites, and so on are aluminosilicates, which have higher proportion of lithium in them, and we use them as a source for lithium. How about the other critical metals, like, for example, cobalt and so on? Usually they will be found in association with other sulfides. So maybe someone is trying to extract nickel from nickel sulfides. With those, we usually have cobalt, manganese, and these other critical elements as byproducts. So it is common to actually extract some critical elements from some of the sulfides as a byproduct. If we're interested in rare earth elements, again, rare earth elements are used in batteries and electronic devices and so on. They tend to occur in the form of phosphates. For example, if you look at monazite and so on, okay, bastnaesite, monazite, and so on, they are very good sources for rare earth elements. So I'm hoping you learn about all this in your process mineralogy unit, but at least for our purpose, for mineral processing, if you don't necessarily differentiate between a silicate mineral and a sulfide, it's very difficult to talk about mineral processing, okay? Because mineral processing, as I said, is all about trying to separate value from waste. So you need to know where the waste is located. You need to know where the valuable element or the valuable commodity is located. So to generalize, if I'm interested in base metals, I will go with maybe sulfides, which tend to be good sources for base metals. If I'm interested in precious metals, Usually precious metals occur in their own naturally as elemental form, so as native form. So native elements such as Au, silver, platinum, osmium, rubidium, and so on, all of those tend to occur in nature as elemental form. That means they don't form sulfides, they don't form oxides. They are found naturally in elemental form. Okay, so if I'm interested in iron ore, if I'm interested in steel making, usually although you have iron in sulfides, we don't actually extract iron from sulfides. We extract iron from oxides. So in this case, hematite, magnetite, limonite, goethite, and all those oxides are very good sources for iron because they can contain up to 60%, 65% iron in them. Okay, so again, just to reiterate, if you find an iron sulfide in an ore, like pyrite, for example, usually the pyrite is a gangue unless it contains gold. Some gold, or actually free milling gold, tends to be bound with pyrite. When it's bound to pyrite, that's an iron sulfide, then because it contains gold, it becomes valuable. But if it doesn't have gold in it, pyrite is usually considered as a gangue mineral, although it is a sulfide, because we don't extract iron from a pyrite. Okay. So obviously in this discussion, I'm not including other common minerals that we dig from the ground, which we use in building blocks. Okay. For example, in Ethiopia, we have a lot of these other minerals that are not necessarily used to extract value from, but they're used for building, for road making, and all other things. So I'm not including those in this discussion of mineral processing. Okay. So again, as I said, the vast majority of deposits that we dig from the ground are aluminosilicates. In fact, about 98.5% is made from aluminosilicates involving oxygen, silicon, and aluminum, which is the aluminosilicate. And in that aluminosilicates, you also have a large proportion of iron, magnesium, calcium, and so on. But usually, those are what we call rock-forming minerals, and we do not extract iron from them. We do not extract manganese and magnesium from them. They're usually gangue waste rocks that are found in association with our target minerals. From economic reasons, what we're interested in is at least whatever we mine from the ground are, for example, nickel, copper, zinc, lead, silver, titanium, and so on. And these ones are usually found only in small amount distributed all over the silicate. Okay, so the distribution can vary from one deposit to another deposit. Some deposits have very high amounts of gold and silver in them. Some have very low amounts of gold and silver in them. And therefore, when people talk about deposits, when we talk about, for example, deposits of gold in Adola region, so what we're saying is in that area, we have very high concentration of gold. Okay, maybe 2 parts per million, maybe 10 parts per million. So that's high concentration of gold found in those deposits. That's why we go out there and specifically look for those with higher concentration of the commodity that we're interested in. Okay, so obviously we need to understand how silicates behave to be able to separate them and reject them, okay, from the deposit. And depending on what type of silicate you are referring to, they could be of different families, they could have different structures, and therefore, based on the structures, they can possess different challenges during mineral processing. Okay, so for example, olivine, as I mentioned earlier, is a magnesium silicate, can have significant amount of iron in it. Okay, this is made from isolated silicon tetrahedron. Okay, if you're looking at a pyroxene, they're made from single chain structure. If you're looking at amphivols, they have double chains in them, and these double chains are usually linked with iron, calcium, magnesium, and so on. If you look at mica, I don't know if you guys have seen what mica looks like. Maybe you can Google it and find what it looks like. So mica is made from a layer upon layer upon layer of sheets of mica, and those are bonded through very weak van der Waals force. You can actually peel it like with your finger, okay, very easily, okay, or with a knife. You can easily uh, try to peel it layer by layer because the layers are actually bonded together through very weak bonds. Okay, and feldspar, quartz, and all the other plagioclase silicates actually are made from framework structures. In, for example, the case of quartz, it tends to be very hard, so it will give you a hard time during grinding and so on. So why am I talking about silicates, although they're considered the gangue minerals? Because we need to understand how they behave during processing. For example, if you have mica, as I said last time, the mica is very difficult to grind, and it's also very difficult to separate from the target mineral. Okay, because we normally use water for processing, and the mica is easily floatable, and it's very difficult to separate from the target mineral. So that's why it becomes challenging. Some of them are clay minerals, and therefore if you have clays tend to be very fine. When you do grinding, they tend to be very fine, and therefore when you have very fine particles, they make the pulp very viscous. It doesn't move very well in processing plant, and that becomes very challenging. And when you try to do settling, the clays don't settle really well, so separating them from the target becomes a lot more challenging. So understanding what type of silicate is involved in your processing operation is very critical because it helps you predict how the processing is going to continue. And sometimes just because of the challenges from the silicates, you might actually have very specific processing plant that can handle the silicates that you have in the ore. Okay, so it's not just about knowing what target mineral you have in the ore, it's also understanding what gangue minerals you have in the ore. So I said also, in addition to silicates, carbonates are very abundant. They can be found together with the target minerals. So as I said, maybe dolomite, magnesite, some of these may have value in construction materials and so on. But generally in mineral processing operations, they're considered as a gangue. Okay, so some of these carbonates like calcite, magnesite, and so on actually are very challenging during processing, and they're very common occurrences in nickel sulfide ores. Okay, when you have a nickel operation where the nickel is in pentadite, usually those contain calcite, magnesite, and dolomite as gangue minerals, and those pose significant challenge during processing. Other carbonates, which contain zinc, lead, and copper, actually are beneficial. Okay, so we can actually have value extracted from zinc carbonates or lead carbonates. But in particular, the copper carbonates like malachite and azurite are very good sources for copper. And sometimes they contain up to 20% copper in them and is high value. And usually maybe for the first couple of years, you can get very high value return from those copper carbonates because of the high amount of copper in them. But generally speaking, again, when you have carbonates in the ore, in mineral processing specifically, we consider them as challenges to processing. Okay, so probably when I talk about mineral processing in this course, I'll be mainly focusing on ore minerals. So when I say ore minerals, we're talking about native elements, sulfides, and oxides that are associated with other silicate material. Okay, so as I said, in this case, native elements, gold, precious metals, and so on, sulfides mainly for base metals, and oxides mainly sources for ferrous metals such as iron, manganese, chromium, and so on. Okay, so we need to understand what is found in what, so that we can predict processing performances better. Another factor we need to consider is based on what you have in the ore. Okay, as I said earlier, minerals are made from very specific atomic arrangements with unique crystal structures and with unique compositions, which means they have very unique physical properties associated with them as well. Okay, so for example, if you look at azurite, which is a copper carbonate I showed you in the previous slide, it is a very deep blue colored mineral. So sometimes color can be used to identify some of these minerals. If you look at malachite, it's a green copper carbonate mineral. Okay, so color can be used as a way of identifying what you have in the ore. So that's one, but not always. Sometimes color can be deceiving, especially if you have impurities in the ore. Color can be very deceiving and it can give you the wrong information. But generally speaking, we can use color as a way of identifying what we have in the ore. But recently as well, due to the advancements in technology, we're actually using ore sorting as a way of beneficiation. And in ore sorting, some of the sensors actually use color, okay, to predict what to reject and what to recover. So color can be sometimes used as a way of not only identification of the mineral, but also as a way of beneficiation, especially if you're using sorting. Luster, if you're not familiar with this word, it actually tells you how shiny a rock looks. And typically, sulfides are very lustrous. Okay, when you pick a pyrite, for example, which is an iron sulfide, they appear very shiny, and people actually call it fool's gold because it looks like a gold. And therefore, that shininess or lustrous properties of pyrite is associated with the fact that it's made from sulfides. And when you investigate a little bit deeper, it's because of the metallic bonding in the metal to sulfur that is found in these sulfides. So the metal to metal bonding or the metal to sulfur bonding, which is a covalent bonding, gives rise to these lustrous properties. Cleavage is the way a rock breaks, okay, during grinding. Okay, some are one-dimensional, some are two-dimensional, some are three-dimensional. So when you actually crush and grind the rock, based on the crystal chemistry of that rock, it actually results in particles that are either one-dimensional or two-dimensional or three-dimensional. Why is it important? It is important especially when you do grinding. Okay. Hardness, obviously, is a key consideration during comminution or during grinding because it predicts how much energy you're going to spend during grinding. Tenacity is probably a more general term that we use to predict how difficult it, for example, some minerals can actually bend and rebound, so they are a bit elastic, some are not. Okay, you can cut some into knives, you can make some into a wire, and so on. So tenacity actually represents all of those properties of a mineral, like elasticity, which is an ability to bend and rebound back, and the ability to be drawn into a wire and things like that. Okay, such as, for example, the copper metal can be drawn into a wire, and I'm sure you have plenty of that in your home for electricity and so on. So tenacity can also predict how challenging comminution can be. Specific gravity is more useful in gravity separation. So some particles are dense, some minerals are light, so gravity separators can operate based on differences in gravity. Okay, magnetic properties, again, obvious. Crystal habit, again, crystal habit refers to during the geological formation, minerals may have unique features. Okay, the way they appear to someone externally is what we call crystal habit, and again, that can be used as a way to identify and characterize minerals. So, to your surprise, we actually use a lot of these properties of minerals, and we exploit those properties of minerals to separate them from one another. Okay, so when you think about it, people came up with gravity separators or magnetic separators and so on because of that intrinsic properties of the minerals. Okay, because we know some are heavy, some are light, so we use gravity methods. We know some are magnetic, some are not, so we use magnetic properties for magnetic separation. Okay, and color, as I said, because all sorters can pick some colors and not the others, they can be used for beneficiation. So we rely a lot on the physical properties of minerals for processing. So that's just what this sentence here is saying. Okay, so physical properties of minerals are important in mineral processing because they are the basis for mineral beneficiation. Okay, so obviously I don't want to talk about beneficiation straight away before I actually tell you about some of those properties, physical properties of minerals that we're exploiting during processing. So that's why I'm mentioning this. But again, I'm hoping your process mineralogy class should probably cover a lot of these properties of minerals, how we use them for characterization, identification, and so on. That in mineral processing, we all try to use that property for processing. Okay, so again, crystallography is a a process mineralogy topic, but why is it significant here? We can use crystallography for characterization and identification of minerals. And for those of you familiar with XRD, a very old technology, just because we know how atoms are bonded together, okay, the way atoms are bonded together will give rise to crystal planes. And by subjecting these crystal planes to X-ray, okay, so we subject the sample to an X-ray at a given angle based on what is reflected back from that angle, we can actually characterize and identify various phases in the sample. And we could say this mineral has that, this mineral has got, sorry, this sample has got this mineral, this sample has got this mineral, and so on. So crystallography is one of the key features that we use for characterization. Because I'm talking too much on the slides, I probably have to go a bit quicker. I think the best way to do is for you guys to ask me questions every now and then. Otherwise, I think I will be here forever if I just keep talking about some of these things. So how do we use X-ray diffraction for mineral identification? As I said, crystallography is the key. And when I say a cubic structure or a monoclinic structure of a typical mineral, what we're saying is there are a number of planes making up that crystal structure or that crystal system. So I introduce an X-ray each of those planes and I record whatever X-ray bounces back from each of those planes. And using Bragg's equation, you can work out the space between those planes. And these planes are unique for every mineral. So if I say pyrite, pyrite has unique planes in its structure. If I say chalcopyrite, it has unique planes. So based on whatever is reflected back, whatever X-ray is reflected back, at what angle, we can work out the spaces between those planes. And from those spaces, we can actually work out what mineral we're looking at. So it's very accurate. It actually can tell you exactly what you have. And not only works for individual minerals. If you give me 5 different minerals in the sample, I can actually work out all the 5 minerals that you have in the sample. And sometimes from XRD, you can also work out quantity. So you can do what we call quantitative X-ray diffraction. And that tells you how you can predict or how you can work out various mineral phases that you have in the sample. Okay, so how are minerals made or how are mineral structures made? I have already mentioned some of these in the previous slides, but there are 3 factors that actually determine mineral structures. The first one is what bonding you have in the minerals. So how the atoms are bonded together. Okay. So you could have different types of bonding, and this bonding that you have between atoms can actually determine what structure of mineral you're seeing, the size of the atoms itself, okay, and the way they pack together. So these three are very critical in determining crystal structures. And why are crystal structures important? As I just mentioned, because once you know the structure, okay, each mineral has unique structure in it, can be used as a way of identifying them. So when we say bonding, there are 4 different types of bonding. I'm not going to talk in detail about each of these. I'm sure you are all familiar. But in minerals, we have similar bonding, okay? So whatever bonding like ionic, covalent, and so on, that you learned in your chemistry classes, those also exist in minerals, okay? And therefore, they would determine how a mineral appears. And obviously, that can be used as a way of identification. Again, the size. Okay, in this case, you have different size atoms. When you say sodium or calcium or zinc or potassium, they're all different sizes. And therefore, the way they pack together will determine how they appear. Okay, if you have a sodium and chloride bonding versus a potassium and chloride bonding, the chloride is common, but the sodium and the potassium are different sizes. Okay, again, that will determine how a sodium chloride appears and how a potassium chloride appears. So again, size is very, I'm not going to talk about ionic radius or covalent radius and so on. Maybe this is again beyond what we intend in this unit. Another significant factor, as I said, is how we pack the atoms together. Okay, so in this case, if you look at native gold, it is what we call a cubic close packing, ABC close packing. If you look at bismuth, for example, it is a hexagonal close packing. And again, based on how the atoms are arranged with one another and how they pack together, that will determine their structure and how they appear. And obviously, the other factor is the electronegativity between the atoms that are bonding together to make up the mineral. Okay, so if the atoms have large electronegativity differences, you tend to form ionic bonding. For example, sodium and chloride have a very wide electronegativity differences, and they tend to form ionic bonds. If they have similar electronegativities, they tend to form covalent bonds. Okay, so typically this is formed between a metal and a sulfur and so on. And elements with small difference in electronegativity tend to form either ionic or covalent, but they will be predominantly covalent. So again, that's how this can be used and manifested in minerals. For example, when we say metals like gold and silver and so on, they are actually dominated by covalent or metallic bonding. When we say oxides, the oxides, for example, could be a manganese oxide. Okay, in this case, the manganese has a high electronegativity, sorry, low electronegativity, and the oxygen has a high electronegativity. They tend to form an ionic bond. Sulfides, usually between a metal and a sulfur. Yes, there is difference in electronegativity, but it's not a huge difference. So that's why they tend to form covalent or usually covalent and ionic mixed bonds. Why is it important? Why am I talking about this? Because in oxides and silicates and carbonates, because ionic bonding is dominant in them, they tend to have high melting point, they tend to have low electrical conductivity, they have low magnetic susceptibility, and they are not lustrous. So why do you care about all these properties? Because on the contrary, the metals and the sulfides are dominated by covalent bond, which means they have high electrical conductivity and high magnetic susceptibility. So as I was saying earlier, most of my valuables are in metals and sulfides. Most of my gangue or waste rock is in silicates. And now I have these contrasting properties. So the silicates have low magnetic susceptibility, the metals and the sulfides have high magnetic susceptibility. So I can use magnetic separators to separate one from the other. Okay. And the same with electrical conductivity. And again, the other factor is because metals, such as precious metals, are made from gold and so on, they're very dense compared to silicates, which are made from silicon and oxygen. So the silicon and oxygen are small atoms, they are light, while the metals are bigger and denser. So they have significant difference in specific gravity, which again can be used as a way of separating one from the other. So that's why properties of all minerals are very critical in mineral processing. So that's why I want to talk about this one again before we talk about mineral processing operation, but in this course specifically about comminution and screening. So because I'm talking a lot, maybe I will pause for a minute and see if anyone has a question. Any questions? As we did last time, maybe you can come close to the mic and talk.
Go ahead, no question.
No questions? Okay. So native metals, typically gold group and platinum group elements are what we call native metals, and they're found in elemental form. So the gold group contains copper, gold, and silver, and the platinum group contains platinum, palladium, rhodium, ruthenium, osmium, and iridium, and these are generally called platinum group elements. And as you can see in that periodic table shown there, from geochemistry point of view, they're also called siderophiles because they tend to form or they tend to occur in nature as metallic form or metallic state. So if you dig something which is mainly a gold ore from the ground, okay, and if you put it through maybe a microscope for characterization, and if this is rich in gold, it's not surprising to see gold grains in that rock. So that photo that's shown there is actually a coarse gold grain running through a sulfide. And this is shown there because, as I said earlier, instead of having a gold sulfide, usually the gold in nature is found in elemental form. And you can actually see that in a microscope, okay? If it's copper, you can find copper in elemental form as well as native copper, but it's not very common. Usually copper is found in sulfur as copper sulfides or in oxides like carbonates and so on. But because you can find elemental copper as well in nature, it is categorized in the gold group. The other element is silver. Again, you can see silver found in elemental form running through the various sample positions, and that can be picked up easily in the microscope. Again, instead of having silver oxide or silver sulfide, usually what we find is a silver, elemental silver. So in mineral processing, you could actually just crush this, grind it into small size, and use a density separator to get rid of the gunk. Okay, so the way it occurs determines what needs to be done during processing. The platinum group elements, as I mentioned, are those 6 elements there, and they actually have very similar properties to that of iron, cobalt, and nickel. And usually when people mine for nickel, they tend to find cobalt with it. They tend to find platinum group elements with it. So the platinum group elements here are actually byproducts of nickel operations. Okay, so this is one of the other things you need to consider. So when you say, I have a nickel mine, yes, the main commodity is nickel, but you should also look for any potential byproducts, because we know naturally nickel has very close association with platinum, palladium, and so on. So you should do proper investigation, do quantitative analysis. Yes, you determine the nickel, but also you need to look if there is any potential byproduct, such as platinum and palladium. Because of that common properties, they tend to found in nature as byproducts of nickel mines. Another occurrence of platinum group elements, including gold, is actually alluvial deposits. Okay, so alluvial deposits are maybe an easiest way to describe them is what you see around seashores as beach sand deposits. And usually that is already a decomposed sedimentary or igneous rock, which over many millions of years has been carried to the seashore. And what you have there is actually a decomposed silica sand and heavy elements or precious elements like gold and platinum. So in places like Russia, for example, if you go to the Ural Mountains in Russia, where they have a very high alluvial deposits of gold and platinum group elements, you can pick a sample, you can look through a microscope of that grain, and you could actually see the platinum and the gold, which are very visible under the microscope. So in those situations, what you have is a silica sand, which is very light compared to the gold or platinum containing grains. So you can use gravity separator easily to separate one from the other. Okay, so those are native elements. So for sulfides, as I say, sulfides represent a metal to sulfur compounds. And in this case, can be generally described as MX, where the M is a metal and the X is sulfur primarily, but it can be arsenic, it can be selenium, it can be antimony, it can be tellurium, and so on. Okay, so typically when I say sulfides, it is a metal to sulfur compound. But usually the arsenic, the selenium, the antimony, and so on also behave similar to the sulfur. So you can have a lead sulfide in nature. You can also have a lead telluride in nature, for example. Okay, you can have a nickel sulfide in nature, but you can also have a nickel arsenide in nature, because some elements behave like sulfur and they will be found in association with the metal. But the vast majority of what we extract from the ground as a valuable ore actually are sulfides, but you can have other elements bonded to the metal as well. Okay, so maybe some of them are made from double salts. If you look at, for example, energite, which is a copper mineral, you can have copper sulfide and arsenic sulfide together to make up that energite. Energite is a primary source for copper, but also when you have high proportion of arsenic, that can be problematic, because arsenic in nature is toxic. Although you are trying to extract the copper, obviously you need to also safely dispose the arsenic as well, and that comes with a cost. Okay, so those who tend to form sulfides in nature are those elements shown there in that periodic table. Okay, so already what I'm trying to tell you is, if you're interested in some of those commodities, okay, if someone is interested in extracting zinc, the primary location they should be looking for is a zinc sulfide. Okay, because those are the ones which contain a high proportion of zinc in them, and naturally zinc occurs as sulfide form. So that's why When we talk about zinc ore or zinc deposit, typically we're talking about a zinc sulfide. Okay, and as I said, zinc sulfides such as sphalerite are common sources for zinc. Again, this is probably more related to your process mineralogy class where you probably can learn a lot, but generally there are a number of different type of sulfides. Some have metal excess sulfide, which is two metals to one sulfur. For example, chalcocite, two coppers and one sulfur can make up the sulfide. Okay, or maybe three metals and two sulfurs. Okay, so in this case, for example, stibnite, which is antimony sulfide. You can have monosulfide like lead sulfide, disulfide like pyrite, and so on. And some of them are rare, some of them are common. Okay, like some of them are a lot more abundant. And as I said, generally speaking, when I say sulfide, although it is a metal sulfur chemistry that we're mainly talking about, it's possible that some of that sulfur could be replaced by an arsenic or a tellurium or so on. So a typical sulfur structure here is shown, a monosulfide, which is represented by sphalerite. As you can see, this is a simple cubic structure where the sulfur is bonded to the zinc in tetrahedral form. And this actually predicts or represents the way a sphalerite looks like. Excuse me. And because of that zinc to sulfur covalent bonding that I mentioned earlier, even though it's not very lustrous like pyrite, sphalerite has some lustrous properties as well. That is because of the fact that you can have metal to sulfur bonding, which is dominated by covalent bonding. So it is very difficult to find a zinc sulfide in pure form. Although I write zinc sulfide for sphalerite, actually in nature what you find is zinc iron sulfide. Okay, so when you do take a sample of a zinc deposit, you do assaying, you have lots of zinc, lots of sulfur, but sometimes you have lots of iron with it. And you might wonder, where is the iron coming from? My XRG is saying it is a sphalerite, and sphalerite is zinc sulfide, but the iron can actually be incorporated in the crystal system by replacing the zinc. Okay, so those purple atoms shown there in the crystal structure can be replaced by iron. And so in this case, you can talk about variety of sphalerites. Some of them have small amount of iron in them. Some of them have lots of sphalerite in them. So again, the value of the sphalerite can depend on how much iron you have, okay, in the mineral. So we'll talk about solid solutions later on, but this is one example of solid solutions. So I mentioned disulfides such as pyrite and arsenopyrite. Again, instead of an atom of sulfur there, typically in the structure you have sulfur-sulfur pairs making up the crystal structure. Okay, so in this case, pyrite is made from an iron and two sulfurs bonded together, occupying the positions. So it's similar to a sodium chloride unit cell, but instead of, in this case, the chloride is the same as the sulfur, but the sodium, for example, in this case, is replaced by the iron. Okay, so instead of one chloride atom position, you can have two pairs of sulfur atoms which occupy that position, and that eventually would give rise to a pyrite unit cell. Although that is the case, still it doesn't distort the structure of pyrite. It is still cubic, okay? And usually when you pick a sample of pyrite, you can actually see those nicely shaped cubes on the fragments of a pyrite because of its cubic structure. So you could probably say most sulfides are derived from basic structures. For example, a lead sulfide is derived from a sodium chloride structure. Maybe you could say some of the sulfide derivatives like chalcopyrite, stannite, and so on are derived from simple structures of zinc sulfide. Maybe I don't think this is very critical for mineral processing, and this is something you could probably consider in process mineralogy again. But for me here, what I'm trying to maybe indicate is most sulfides are simpler in structure. More complicated sulfides are derived from these simple structures. But in any case, the way the sulfur is bonded to the metal will actually have consequences on the way it appears externally and the way it appears or behaves in a typical mineral processing operation. Okay, I can talk about these ones if anyone has an interest. And this is typically what I go through for my process mineralogy class. So another type of minerals are oxides. Again, obviously, as the name implies, oxides between a metal and an oxygen. Because of that, sufficient differences in electronegativity between a metal and oxygen, typically ionic bonding is predominant. And because of that, these are non-conducting, generally speaking, and they don't have metallic luster. And naturally, these are sources for chromium, manganese, titanium, iron, and so on. And some of the examples are shown in that slide there. Okay, so hematite, magnetite, goethite, and so on are iron oxides, which we normally use for extracting iron from. Ilmenite, rutile, and so on are good sources for titanium. Again, these are what we normally call heavy mineral sands or beach sand deposits. And these are common sources for not only titanium, but zircon and rutile and zircon and other commodities that we use for making aircrafts, space shuttle, and things like that, and alloying and so on. And typically titanium is extracted from them, and they're common around beach area, and that's why we call them beach sand deposits. Chromite is a good source for chromium, the name implies there. And there's a good example in South Africa in a place called Bushveld, where a chromium is predominant. And in addition to chromium, sometimes you can find platinum group elements in chromites as well. So again, not only source for chromium, but also platinum group elements. As I mentioned earlier, copper tends to form carbonates, and copper tends to form oxides as well. For example, copperite can be an example of a copper oxide. But typically in a given copper Okay, yeah, I think randomly mute TR again Wandande, that's what. So for those from geology, you probably are familiar with different ore zonations. You have the Goshan, you have the leached zone. If you go a bit deeper, you have the oxide zone. And in the oxide zone, you have dominantly copper oxides. Okay, and in this case, the copper oxides can be in the form of malachite, azurite, and so on. As you go a bit deeper, you find the transitional zone and the supergene zone, where you have sulfides predominantly. Okay, so for a copper, that could be predominantly, so chalcopyrite would be the dominant one, but you can have chalcocite and a number of other secondary sulfide. And as you go deeper, you find the primary hypogene zone. That's where you have the primary mineralization. So again, depending on where you are during your mining, if you're close to the surface, you most likely are likely to find oxides. If you go deeper and deeper, you are more likely to find sulfides. And I'm talking about typically base metal deposits in this case. Okay, so maybe if you're doing an open cut mine, maybe the first few years, you might be looking at mining the top area, which is dominated by oxides, and that could be a good cash flow. But as you go deeper and deeper, we know that's where you hit the sulfides. So your processing plant should be able to handle sulfides. because maybe for 20 years, for 30 years, what you're going to mine is actually the sulfide zone, and therefore the processing plant should be able to handle sulfides and should be suited to process sulfides. Tantalite, columbite, and so on. Maybe you guys might have heard Kanticha in Ethiopia, in the southern part. I'll talk about that in the next slide. But tantalites, columbites, which are sourced for tantalum and niobium, tend to also be found in oxide form. Okay, and a number of others, including uranium oxide, manganese, and so on. So, I'm sure you are aware of Kanticha, which is a pigmatite deposit. Okay, so mainly dominated by columbite and tantalite, significant amount of niobium and tantalum in them. So we actually did a few papers. We published a few papers on this topic. So if you guys are interested, you can maybe find those by Googling the papers. But what we did was try to characterize the samples from this area, determine the composition, and that's mainly dominated by tantalum. Some places we have tantalum oxide in them, and some ones had about 30% niobium oxide in them. So in addition to that, there's also significant spodumene in them, but I don't believe anyone in Kanticha is looking for extracting the spodumene or the lithium from. But I think at the moment, people are just doing small operations where they extract the tantalum and niobium, they concentrate, and I think basically ship it, most likely to China. So in addition to that, you have gangue minerals like beryl, albite, feldspar, and muscovite, which is a mica. And so your typical processing would include some kind of gravity separation to get rid of these silicate minerals. So as I was saying, these are some of the um, analysis we did. And if you look at that table below the figure, so you have tantalum there, you have niobium there. Can you guys see any issues in processing an ore from Kanticha? Okay, so if you look closely there, there's some uranium there, and there's also some thorium there. So those are actually radioactive, and you can't just process the ore, concentrate the tantalum and niobium, and ship it because of the radioactivity associated with that ore. You need to find a way of removing some of those radioactive elements like uranium and thorium. Okay, otherwise you will pay some penalties. So some of the papers we published were actually trying to look for ways of removing the uranium and the thorium from the concentrate before you can actually ship it. Okay. So again, in mineral processing, that's the other thing I'm trying to always talk about. So yes, you may have a value in a deposit, and you may have a processing plant that can handle that. But it's not just about the valuable part, it's also looking at some of the toxic elements associated with it and how you capture them in the processing plant, or sometimes just looking for some extra byproduct like gold and platinum and so on. And to be able to do that, your plant should be accounted for the target as well as the toxic and the precious metals as well, and you should incorporate that in your processing plant. Okay, so to summarize this part, so obviously depending on how minerals occur, depending on what we want to extract, there are some key properties that we can look for, and based on those key properties, we can somehow gauge our mineral processing plant to maximize recovery of the valuable commodity. In addition, we can also design appropriate tools to remove some of the toxic elements associated with it as well. But the vast majority of our mineral processing plants are actually based on some of the unique properties of the minerals. Okay. So I will talk about solid solutions next, but anyone with a question, it's probably a good time to ask now. Yeah, go on.
From the previous slide, you said pyrite taken as a gang material, it does not contain gold and can
Yeah,
beneficiate iron from it. May I know why there is it? Is that due to the low concentration of iron or the complicated nature of beneficiation?
um,
First question.
are you asking about the iron sulfide? I can't hear you very well, so I'm hoping you're talking about the iron sulfide.
Yeah, the iron
Okay.
sulfide,
Yeah,
pyrite.
yeah, yeah. Yep.
We can't beneficiate iron from it, and we taken as pyrite as a gang material unless
Yep.
it's gold.
Yep. Yes.
Why we need to beneficiate iron from it? Is that due to the low concentration of iron or the complicated nature of beneficiation?
It's mainly to do with beneficiation because the iron is bonded to the sulfur. You can separate the pyrite, but leaching is going to be very expensive, so we're not going to do that. And smelting is also difficult because the sulfur actually creates lots of problem during smelting. So that's why people actually extract iron from the oxides, because typically once you concentrate the iron, you do smelting to make steel anyway, and oxides are by far straightforward, but iron sulfides are very complicated. So we don't have actually a proper commercial process that can handle iron sulfides.
And the other question
Yeah.
from the physical properties of minerals, let's
Yep.
tell how can I use it as a means of beneficiation? Is the best I can. Maybe that's for identification of minerals, but I'm a little bit confused. How can I use the means of
Yeah.
beneficiation?
If you can please come close to the mic. I can hear some part, but I can't hear
Oh, okay,
everything that you're saying.
let me repeat.
Yeah.
As you said,
Yeah.
from the physical properties, the luster and color, we
Yeah.
use that as a means of beneficiation.
Yes.
How can I use? Maybe we use as a means of identification of minerals,
Yeah.
but I'm a little bit confused on how can I use as a means of
Okay. Yep. Yeah. Fair enough. Yeah. So what is it? So we're talking about this one here, right? So physical properties can be used for identification of minerals. Okay. So that is one of the benefits of physical properties. So this is, maybe you go out there, you're looking for, I don't know, maybe some kind of base metal. Okay. So you go out there, you take a sample of something, you want to know what's in there. Before you even do very complicated analysis, you can just look at the sample, and if you have sulfides there, they appear to be very lustrous, for example. They're very shiny, they have some unique properties, and that can be used for identification purposes. So here, we're not talking about processing, just identification. And again, you can use color, although as I say, color is not always correct, but it can be misleading. But for some elements or for some minerals, color can be easily used for identification. All of these properties actually can be used for identification of minerals. Okay. In addition to that, so this is for identification, but in addition to that, we can also use these properties of the minerals in processing. Okay, for example, in processing, density is one of the key factors. So density separator can be used. But not only that, you can, for example, use cleavage, hardness, and tenacity to predict how the ore behaves during comminution and during grinding. Okay. Why is that important? Because that actually will determine what type of crusher or what type of grinding mill I need to buy to be able to handle this type of ore. Okay, so if it has three-dimensional cleavage, okay, chances are when you crush it, it just breaks into various different pieces, irregular shapes everywhere. But if the cleavage is one-dimensional like mica, usually it is a flat layer by layer kind of mineralogy, gives me challenge during processing or during crushing and grinding. So all I was trying to say there was these physical properties are good for identification, but they also tell us a lot during comminution to predict how they behave during comminution. And based on those, before I even do experiments to investigate and do metallurgical work, I can actually say, okay, maybe I would say crushing is straightforward for this ore, or I would say crushing is a lot more difficult. Let's think about what kind of crusher we're going to buy. So they actually tell you or actually inform you how you're going to go and process those. And that's why I say, yes, identification very critical, but also for processing very useful. You can use magnetic properties. If you have, for example, magnetite in the sample, you can easily pick it up. If you have ilmenite, you can pick it up easily in the sand, for example. If you have pyrrhotite, you can easily pick it up with a magnet and identify it. So magnetic properties can be used for identification of minerals. But as I said already, magnetic properties are also useful for processing. Okay, I hope it makes sense. Maybe I confused you earlier, but we use it for both purposes. Okay, any other question? I think someone is trying to ask question from the back.
Yes, I have a question. Okay, my question is regarding the classification of minerals as ore and rock forming minerals.
Yeah.
In classification of rock forming minerals and ore forming minerals.
Yeah.
What are the basic criteria as a minerals being an ore minerals or
Yeah.
rock minerals? What are the interests?
Okay, yep. So very good. So when we say rock forming minerals, we're typically talking about silicates. So aluminosilicates, which are the vast majority of what we dig from the ground. Okay, so these are considered gangue minerals. They are waste rocks. And some examples of the silicate minerals are shown here. So olivine, pyroxene, and amphibole, mica, these are all silicates that are found in association with the ore-forming minerals. What are the ore-forming minerals? The ore-forming minerals are the ones which have some value in them. Okay, so when I say value, such as titanium, nickel, copper, and so on. And usually those ones are the ones I said occur in native form, for example, gold, or in sulfides. So for example, copper, chalcopyrite, chalcocite, and so on, or for zinc, sphalerite, and so on. So these are minerals, typically sulfides, that are actually used to extract value from, and that's what we call ore minerals or ore forming minerals. So rock forming is more silicate based gangue versus ore forming is more sulfide, oxide, native metal type, which we actually extract value from.
Sorry, my question is regarding the two. For example,
Yeah.
rock forming minerals. For example, quartz is one type of rock forming minerals.
Correct.
These rock forming minerals have a possibility to being as an ore mineral. For example, the companies have interested on silicon.
Yeah.
Silicon.
Yeah.
In silicon, want
Yeah.
to produce or product
Yeah.
silicon semi-metals.
Yeah.
In this case, the rock part is being an ore mineral.
It's still rock forming mineral. Silica is a rock forming mineral still. So I think what I'm trying to say is when I say ore forming, I'm talking about sulfides, mainly predominantly sulfides. And we're talking about metals, base metals, precious metals that can be extracted from them. So I'm not saying the rock forming ones don't have any value in them. Okay, so if you look at carbonates, for example, back home, usually carbonates are limestone and things like that are actually oxides, are actually like they're considered like minerals, but we call them industrial minerals rather than the ones that we normally categorize as minerals. So although we say silicates in mineral processing generally, those are actually what we consider as a waste. If someone is interested in silica, which is, for example, used in glass making and things like that, you can extract silica from anywhere. Okay, so if you have a vast majority of the ore containing silica, sometimes 20%, 30%, we can actually concentrate silica. But we're not saying silica is an ore forming mineral in this case. Okay.
My question is regarding about processing.
Yep.
About tantalite, you say something about tantalite.
Yeah.
In the processing of tantalum,
Yeah.
radioactive elements like thorium and uranium will be released.
Yeah.
Is there any process technology that will concentrate these radioactive elements and use for nuclear energy as a source?
Good question. So in this case, when at least in this example, what I was trying to talk was about the pegmatite deposits, which we normally use for tantalum and niobium extraction. In those, we have trace amounts of thorium and uranium. So these ones, you don't economically concentrate them and extract the uranium and thorium from. So these are actually considered toxic elements. They actually are something you need to remove from the concentrate. They're not in economic amounts. If you're looking for a uranium deposit, okay, so you should be looking more into specific ore deposits of uranium. Sometimes uranium is found with base metals. For example, in Australia, they have a place called Olympic Dam, where the primary commodity is copper and gold, but uranium is found in high concentration, so it will be possible to economically extract the uranium as well. But in the Kandicha example, because uranium and thorium are very trace amounts or very small in amount, you can't actually concentrate it for value. Okay. So in that paper, you can see that paper down in the slide I put in there. What we did was try to wash the concentrate with weak acid and weak base to actually remove the uranium and thorium, not about concentrating the uranium and thorium. Okay. Does that make sense?
Yes.
Yeah. So the quantity will matter eventually. If it's just a trace amount, then it's a problem. You have to get rid of it. If it's high concentration, then you can actually have a proper plant to produce a byproduct.
And one more question.
Yeah.
About carbonate and kimberlite. So
Yeah.
as you know, carbonate minerals are formed in the mantle, and it will be derived by magmatic activity and come to the surface. So it contains a diversified type of minerals. They are a lot in number. So how could you be able to, deal their properties. Since they are diversified in number,
Yeah.
it is very difficult just to separate in color, hardness, and so on.
Yeah. So
uh,
yeah. So you need to do proper characterization first. So characterization tells you what you have in there. So what silicates, what variety of sulfides, what variety of oxide you have in there. So if you give me a sample containing lots of silicates, lots of sulfide, and lots of oxide together, you can just use that and characterize it. That's one. But you can actually use a physical separation process first to separate things from one another. Okay, so before characterizing, you can separate the silicates together based on their properties. You can separate the sulfides together based on their properties, and so on. And then I can take the silicate portion, characterize it. I can take the sulfide portion. Maybe I have 5 sulfides there. I can characterize that. Maybe I have 4 oxides. I can characterize that. So you can actually use physical separation methods or beneficiation methods first, produce different streams, and those streams can be analyzed. But usually your XRD should be able to also pick most of, even if you have 10, 15 minerals in one. Sometimes you have peak overlap, and that can be very challenging. But typically you should be able to identify what's what, especially if they are in good amounts. If they're in trace amounts, then it can be a bit challenging. Any other question, guys? No?
yes.
Okay. So the next topic is on solid solutions. I'll talk about that one a little bit. So sharing. Okay. Can you see that slide?
Yes.
Yes? Okay. So, excuse me. So how much or how many of you actually know about solid solutions? Does that even make sense? So if I say a solid in a liquid, for example, if you have sugar in water, you can understand. Okay, you can dissolve a solid in water. Does anyone know what we mean when we say a solid in a solid? So this is actually what we mean by solid solution. Anyone?
Yes.
So for example, if you look at alloys, okay, maybe steel made from some iron, some carbon, and so on. It's actually two solids mixed together. Okay, so you have an iron and carbon or whatever, or even when you look at bronze, something like that. Alloys are usually mixed up, where you have a solid and a solid mixed together to form one as a solid. And that's what we mean by solid solution. So you can actually have that similar property in minerals as well. And I will show you why this is relevant in mineral processing. So in this case, metal alloys probably you're familiar with, where steel, for example, can be made from a number of solids. But in minerals, as I said earlier, when I gave you a definition of minerals, I said they should have some fixed composition. So when I say chalcopyrite, I know copper, iron, sulfur make up chalcopyrite. When you say quartz, you have silicon and oxygen making up quartz. But in nature, you actually find lots of examples where some of the composition of the minerals can vary slightly based on other impurities that they possess in their crystallography. Okay, so as I mentioned earlier for olivine, which is a good example, we said magnesium can be replaced by iron. Just like that, you can actually have lots of other examples, including sulfides, where in nature, one element can substitute for another. So all of a sudden, instead of just talking about zinc sulfide, which is zinc and sulfur, you can talk about zinc replaced by iron, and you have what you call now iron in zinc. And then you have iron zinc sulfide. We still call that sphalerite, but the iron impurity can be very critical. If you have only a tiny bit of zinc and lots of iron, then although you say it's a sphalerite, it will be almost economically difficult to extract the zinc from the deposit. So that's why solid solutions are very important. But sometimes it may be a positive thing. Sometimes you can have gold or platinum and so on incorporated into these minerals. And when that is the case, and if it's in high concentrations, then the gold or the platinum would be a useful byproduct. So depending on what we're talking about, solid solutions can be good or can be detrimental in a given deposit. So you could have substitutional solid solution, you could have partial substitutional solid solution, interstitial solid solutions, and omission solid solutions. So I'll probably briefly talk about each of these. Okay, so the first example in substitutional solid solution is olivine, the magnesium silicate or the iron silicate. So this is naturally formed. Olivine can be found naturally, but you could also have olivine formed during smelting. Okay, especially in nickel sulfide. So once you concentrate the nickel sulfide, the next step down in the processing will be to smelt, to basically burn the nickel sulfide, and you have a melt, and you have a mud and slag, and in the slag you actually form lots of the olivine, which is a magnesium or an iron silicate. And also sometimes the olivine can be actually the primary host of nickel laterites, where I told you last week that nickel laterites will have nickel in the silicate structure, and therefore olivine can be a host. So in this case, magnesium silicate is one end member, iron silicate is another end member. In between that, any amount of the magnesium can be replaced by the iron. So for example, let's say 0.5 of the magnesium is replaced by the iron. So in this case now, you have what we call 75% magnesium and 25 iron making up the olivine. Or you could have one magnesium replaced by the iron. So in this case, you could have 50% magnesium, 50% iron making up the olivine. Okay, so if you have 75 magnesium and 25 iron, that's what we call a FO, which is forsterite, 75, and Fa, which is the firelite, 25%. And we call this a binary solid solution. So we have two end members here. So one is the firelite end member, the other one is the forsterite end member. And between that, the magnesium and the iron can replace one another in unlimited proportions. Okay? So in this case, we say it is a complete solid solution between the magnesium in the member and the iron in the member, because you can pick any proportion. So 80% magnesium, 20% iron, maybe 21% magnesium, 79% iron. So you could have any proportion there between that 100% between the two. You could have various proportion of magnesium and iron replacing one another, and this can happen naturally. Okay, so that's why we call this a solid solution or a complete solid solution between those two in members. So why is it occurring, or why do we see this in nature? It comes down to the crystallography of olivine and one magnesium atom being replaced by an iron atom, and so on. So for solid solutions to occur naturally, there are two requirements, basic two requirements. You can have more, but the main requirements are that one, the ionic side of one should be comparable to the ionic size of the other one. So in this case, the magnesium size should be comparable in size to the iron. If one is too big and the other one is not comparable in size, then they don't actually replace one another in the lattice. Okay. The other is the charge. So both of them, magnesium and iron, have 2+ charge, and therefore that charge balance would also help in the substitution of one with the other. So you can have solid solutions there. So either the size or the valency should be balanced for solid solutions to happen in nature. And that's why it is the case. So in olivine, if you look at iron 2+, its size is about 0.78 angstroms, and magnesium has 0.72 angstroms. So because of that comparable sizes between the two, so if the size difference is less than 15%, then you could have one replacing the other. But if the size is too big, for example, between magnesium and manganese here, because manganese is bigger, they don't actually make a solid solution between the two. But iron and manganese can do the same, because the difference in size between iron and manganese is less than 15%. So again, these are some of the requirements. So what is the fuss about solid solutions? Why do we care about knowing about solid solutions? Because based on how much iron replaces magnesium, olivine, in this case, can be lighter or denser. Okay, for example, specific gravity of pure forsterite is 3.22. Specific gravity of firelight is 4.39. If you have more iron replacing the manganese, the olivine becomes heavier and heavier. So in this case, solid solutions can affect specific gravity. As we know, if specific gravity is different, then based on that, minerals may not be recovered completely. Okay, because instead of being heavy, some are lighter because of that possibility of solid solution. And sometimes they appear different in color. For example, as you add more and more iron into olivine, you have the color changing into darker and darker. So as well, impurities can affect color, appearance, and so on. And sometimes they may even distort the crystal chemistry. Okay, because if you feed a slightly bigger atom, although it's within the 15% range, sometimes that can distort the crystallography or the crystal lattice of a mineral. And again, that will have a significant influence on how the mineral appears. So that's the case where you have complete solid solution, where unlimited amount of iron can replace the magnesium. So in the partial, you have only some fraction of one element replaced by the other. For example, in sphalerite, as I said, sphalerite, pure form of sphalerite is zinc sulfide. But in nature, it's actually very, very rare to find a pure sphalerite. What you find in nature is some sort of zinc iron sulfide. So in this case, the iron is replacing some of the zinc in the crystal lattice. Okay, so up to 50% of the zinc can be replaced by the iron. We don't seem to find anything in nature beyond that, but we know up to 50% of the zinc can be replaced by the iron. So again, if you're looking for a variety of solarites, the valuable one is the one with smaller amount of iron. The other variety of sphalerite with lots of iron in them are actually not economically significant. But in this case, because not every zinc is replaced by the iron, we say this is a partial replacement, and therefore this is a partial solid solution. Another example in sphalerite is cadmium. Okay, cadmium, for example, can replace some of the zinc. Manganese can replace some of the zinc. And so when you say sphalerite, you could have sphalerite containing manganese, cadmium, iron, and so on. So although maybe your XRD gives you, oh, you have sphalerite in the sample, in reality, you actually don't have pure sphalerite. What you have is sphalerite containing lots of other elements in it. Again, what's the big deal here? The big deal is if you have cadmium as an impurity, as a solid solution, then we know cadmium is toxic. When you're going to extract the zinc, you have to deal with the cadmium as well. Okay, especially if it's in high amount. And therefore it needs to be removed, it needs to be treated. And sometimes the cadmium can be really high in amount. You can actually produce a byproduct of cadmium, and therefore that can be a good thing. But typically, cadmium tends to be trace amount, and therefore it needs to be disposed of properly during processing. Another example of partial solid solution is the tetrahedrite tennantite series. So if you are aware, tetrahedrite has 12 carbons, 4 antimony, and 13 sulfurs. If you replace all the antimony with arsenic, you have tennantite. So in this case, the antimony and the arsenic can replace one another in unlimited proportions. Okay, so for example, there you could have copper 12, antimony 2.6, and the remaining replaced by arsenic and sulfur 13. This actually shows the arsenic and the antimony replace one another in unlimited proportions. As I said earlier, if this is the case, then it is a complete solid solution, the previous example I given you. So why I have this under partial solid solutions, it's actually to do with the copper. So the copper also can be replaced by other elements. What other elements? For example, the copper can be replaced by iron, can be replaced by zinc, silver, mercury, and so on. So in nature, sometimes you find, okay, it's tetrahedrite sample or mineral, so that's a source for copper. But when you do investigation, when you do mineralogical studies, you find the tetrahedrite has some iron in it, has some zinc in it, some mercury, some silver in it. Why is that possible? Because we know solid solutions are common occurrences in minerals, and because of that possibility of replacing one another, okay, elements can replace one another because of the size and charge balance, then you can have that variety of composition. Again, mind you, I said at the beginning of this lecture, minerals have either a fixed composition or a variable composition within a fixed range. So in this case, we have copper replaced by other elements, but the sum of all those elements is always 12. Okay, so this is very important. So when you add the proportion of iron, zinc, silver, mercury, and copper together, it's 12. So that's still, yes, there is variation, but that 12 doesn't change. And as I said here, you have 12 coppers. Okay, so that's why the structure is still retained. It is still a tetrahedrite, but some of the copper can be replaced by other elements. So that's why it's predictable composition, but we know it can vary within a given range. And as I said, the same is true for arsenic and antimony. They can replace one another. So again, this actually qualifies for partial solid solution because not all the copper is replaced. Only some of it is replaced. You will still have the copper as the primary element, but only a proportion of the copper is replaced by iron, zinc, and so on. And in some places, actually, the tetrahydrite has very high silver content in it, sometimes up to 40% silver. So in this case, oh yes, tetrahydrite is a good source for copper, but when you look at a given deposit, you can have up to 40% by weight silver in it. So obviously the silver here would be a byproduct. If you have mercury in trace amounts in tetrahydrite, then it is a problem. Again, that needs to be captured and needs to be disposed of properly. Okay, another example of solid solution is interstitial solid solution. So in this case, the atoms don't occupy other positions by replacing other elements, but they simply sit in some void spaces in the crystal lattice. So they just occupy a space rather than replacing an element in the crystal lattice. For example, a good example is chalcopyrite and hycocite. So it's believed hycocite is derived from chalcopyrite, but it contains one extra iron, as that slide shows there. So chalcopyrite plus one extra iron gives you hycocite, but we don't know why that iron is sitting there. So there is always extra iron, but that extra iron actually is not replacing anything. It's not replacing the copper. We still have 4 coppers, and it's not replacing the sulfur because they're incompatible, but there's some extra iron there in hycocite, and that's because the iron simply occupies a void position, a space, and that again can be found in nature and is considered as an example of solid solution. The last one is omission. So this is the opposite actually. Instead of an element occupying a space, there is an element missing from the crystal lattice. If you look at pyrrhotite, okay, in pyrrhotite we have 7 iron and 8 sulfurs. So there's 1 iron missing for every 8 sulfur. It's probably better to see it here in this depiction here. So you can see here there's 1 iron missing there. And we call this omission solution because there is some iron omitted from the crystal lattice. And this actually is very important in processing because pyrrhotite is highly magnetic, and it's highly magnetic because the dipole moment for sulfur cancel one another, but for iron you actually have 1 iron missing, so there will be a net dipole moment, and that will make pyrrhotite highly magnetic. Probably those from geology, you can use this magnetic property of pyrrhotite for exploration purposes and so on. Okay, but the fact that it's magnetic is mainly due to 1 iron missing from its structure. Okay, so again, why important? Why solid solutions are important in mineral processing? Because often you could have trace amounts of extra elements. So this can be either precious or deleterious elements or toxic elements. So as I want to emphasize, mineral processing is not just about extracting the value, it's about also looking at options for byproduct and also looking for any toxic elements that you have. And solid solutions are the main mechanism by which you have either an extra byproduct or a toxic element in the minerals. So in this case, iron, for example, is found in arsenopyrite. Also, arsenopyrite is iron, arsenic, sulfur mineral. Sometimes in some places in gold deposit, you have gold in arsenopyrite. So again, maybe someone is not going to look for gold in arsenopyrite, but in nature we know actually lots of places arsenopyrite has gold in it. Also arsenopyrite in chemical structure, it doesn't have any gold in it. In nature, you actually have arsenopyrite containing gold. So that becomes valuable now all of a sudden. In some places, you have pentadite, which is a nickel sulfide mineral. So yes, we can get nickel from it, but sometimes you have a large amount of palladium associated with nickel sulfide. This is due to solid solutions. So again, we need to characterize it, understand it, and find a way to recover the valuable byproducts such as gold from it. Okay, so if you have solid solutions, and in this case, if you have gold in solid solutions in sulfides, the gold tends to be very fine in size. It's actually almost atomic scale gold distributed in arsenopyrite, pyrite, and so on. So when you do assay, it comes with gold. So you have some gold in the sample. But when you do XRD, it comes as arsenopyrite. There's arsenopyrite, but there's gold. There's pyrite, but there's gold. So you need to do a very detailed quantitative analysis to work out exactly how much gold you have, if it's a gold deposit. Because, as I say, sometimes this can be economic and can be useful to extract the gold from. So in terms of how the iron is going, the gold is going in arsenopyrite, we actually don't have a full understanding because, as I say, in arsenopyrite, we have iron, arsenic, and sulfur. Gold is not going to replace the iron because gold is too big. Gold is not going to replace the arsenic. It's too big. It's not going to replace the sulfur. Again, different properties and still too big anyway. So the only explanation is that gold is just sitting in the space as interstitial solid solution, okay, rather than replacing any of the elements in arsenopyrite. So that's why we have interstitial solid solutions in gold ores, especially those containing arsenopyrite. Okay, anyone with a question so far before I go to the next one? Okay, so if no question, I will probably continue and maybe you can ask questions at the end. So now you brought a sample, maybe you went on a field trip, maybe you are an exploration geologist who is looking for deposits, and maybe you think some area has value. Maybe you want to investigate. Maybe you did some basic observation with microscope with your naked eye. Maybe you did some analysis first, and you are interested in an area or a deposit. So the next step you do is mineralogical analysis. Maybe you send that to a lab. You say, can you please tell me what I have in this sample? Could be, for example, using wet chemistry, where you take the sample, crush it, grind it to very fine particle size, then you dissolve it in an acid and you leach it out, and now you have solution, and that solution can be analyzed. So it can be using AS, it could be using ICP, it could be, you have a number of methods that we can use to determine elemental proportion. Or maybe you just send it for an XRF where you actually have just the powder pressed into either a pallet. Maybe you make some fusion beads. Again, you analyze that. And usually when the results are displayed to you, the person who did the analysis will say, I'm going to give you weight % of whatever you have in the sample. Because if you did XRF, for example, the results come up as weight %. So you have this much copper, this much zinc, this much lead, this much iron, and so on. But from a mineral processing point of view, you want to know how the occurrence of the elements are rather than proportion. So for me, for example, if you say, I'm interested in the copper, I send this sample for copper analysis and it comes to 20% copper. For mineral processing, that is not beneficial at all. So that kind of information doesn't mean anything. excuse me, because yes, I have copper in there, but for me, but for mineral processing, I want to know how the copper is occurring. Is it a copper carbonate? Is it a copper oxide? Is it a copper sulfide? I want to know what copper I'm looking at. Not only that, I also know if you say it's a copper sulfide, I want to know which copper sulfide. Okay, is it chalcocite? Is it chalcopyrite? Is it energite? Which one? Because I know all of these copper sulfides behave differently. If, for example, I'm doing flotation for my beneficiation, I know each of them behave differently during flotation. So for me to have a proper processing plant, I need to understand, not just saying I have copper there, but I want to understand what type of copper. If I say, okay, it's not oxide, it's not native copper, it's sulfide, then I want to also go further and say which sulfide. So mineralogy is very critical and important. So that's why we say qualitative analysis alone is not going to tell you so much. So that's why you need to combine both qualitative and quantitative information to say, yes, I have copper from quantitative analysis, but then from mineralogical investigation, I know it's a copper sulfide, and I know it's actually not just copper sulfide, but it's a chalcopyrite. Then I have this full information. I can then think about processing that. I can have common conventional methods to process the chalcopyrite. But in any case, so in this case, sample comes up, this is the results you get. Maybe you did an XRD, and XRD says it's tetrahedrite. So as I mentioned earlier, in tetrahedrite, you have copper, antimony, and sulfur. Okay? But your analysis came up with a number of other additional elements. The copper is expected, yes, but maybe the analysis says you have silver, you have iron, you have zinc, and so on. So you need to account for what's going on here. Maybe you have additional other minerals in addition to tetrahedrite. That's one possibility. Okay, maybe if you say you have zinc there, it could be that you have sphalerite in the sample. Or if it is iron, maybe you have pyrite, and so on. Or maybe you have chalcopyrite because you have both copper and iron. So you need to know what's going on. And the best way to do this is actually to recalculate based on elemental proportions, weight proportions. We can actually calculate atomic proportions. From atomic proportions, we can work out whether this is just solid solutions affecting the composition or whether these are actually additional minerals in the sample. So if you did that, probably if they've done a good job with analysis, usually if you add all the weight percent, you should get close to 100. Okay, so usually 99 to 100 is acceptable, but we allow for analytical precision. So 0.5% is allowed for analytical precision. Maybe when I add everything, it could be between 99 and 100.5%. But it's also possible that you're missing some trace elements because every equipment has its own detection limit. If you have tiny amounts of other elements that may not be picked up in the instrument, then it doesn't necessarily mean the instrument is wrong. It just means that some of the other elements you have are actually very small in quantity, so it can't be picked up. So we allow another 0.5% for trace elements. So generally speaking, you should ask for the person who gave you the data to expect somewhere between 99 and 100.5% of the total weight percent added up. Now I have this. So what I want to know is to know whether this is just tetrahedrite with solid solutions in it or whether there are a number of other minerals. So I would say, okay, tetrahedrite, I should have about 29. So if you add all these elements here, all atoms, so I have 12 copper, 4 antimony and 13 sulfur. So you add this up, you should have about 29 atoms. Okay, so what I will do then is divide the weight percent by atomic weight for each of them. And then when I do that, I get these proportions. So it's saying all the atoms add up to about 1.8. But I know my atoms should add up to 29 if it's tetrahedrite. So what I will do is I multiply 1.827 by some number, some factor to get 29. So that I multiply each of these by a factor to get to 29. So that factor is 15.84. Okay, so 15.84 multiplied by each of these in the fourth row, or in the fourth column, and I will get the total adding up to 29. So if I did that, multiply everything by 15, I'll get about 9.7 copper, about 0.34 silver. Everything adds up to about 29. So it tells me that, oh, actually there is not much other impurity. It's still tetrahedrite. And then the next step I would do is, now for tetrahedrite, I have a different composition. So I have 12 copper, but my calculation shows only 9.7 copper. So as we said earlier, it means the other missing copper is actually replaced by silver, iron, and zinc. Okay, so that's what this one is showing here. So then I say, okay, I know the silver, the iron, the zinc can replace the copper. So then I want to add 9.7 plus 0.34 plus 0.59 plus 1.4 and see if this adds to 12, which is the copper. You add them up. If it adds to 12, then that's very good. So the other one is I have 4 antimony here, but I have only 2.08 antimony here. So that's actually because the arsenic was replacing some of the antimony. I expected 13 sulfur, I have 13 sulfur. So when you look at it, overall, it's actually because of the fact that the arsenic replaced the antimony, the iron, cobalt, and nickel replaced some of the copper, and some of the sulfur can be replaced by any of these, tellurium, selenium, arsenic, and antimony. But in my example, this is actually not shown. So I don't have tellurium, I don't have arsenic, extra arsenic that is. And therefore, when you add everything up, you should get something like this. You guys okay? I hope everyone is okay. Looks like there's some background noise there. But in any case, so you add them up, you group them, and you get something like this. And it actually is one of a typical example of solid solutions, where in nature, maybe you are not able to find pure tetrahedrite, but some of it is replaced by other things, such as silver, iron, zinc, and so on. So what we're looking for is, we say if the silver comes to be very high, we could say, oh, actually the silver can be a byproduct here. Okay, and so on. If I have mercury or extra toxic elements here, then I know they will be recovered with the tetrahedrite, and that can become problematic. So in this case, my formula eventually can be written by what's shown down there in the slide. Or maybe another expression would be to write every proportion in the formula and say this is what you should expect in your sample. So I don't know if this is a bit too much for you guys, but if it's complicated, don't stress too much about it. what I'm trying to show is that in nature, it's actually possible to obtain byproducts. It's possible to obtain toxic elements incorporated into minerals. And the way we find this is by doing proper quantitative analysis, account for any additional elements that we see, okay, from the qualitative or quantitative analysis, and understand what's going on. Once we understand the mineralogy, then we can talk about processing. So if I know I have a pure tetrahedrite, I can have my proper processing plant for it. But if I know my tetrahedrite has lots of silver in it, then I know silver is a potential byproduct. So it's not just one way that we always process minerals. Depending on what we have in the mineral itself, we can account for possibility of byproducts and so on during processing. Okay, so maybe I brought a more complicated example because most sulfides are actually simple in structure, but I just wanted to demonstrate that you can actually work out some of those proportions from quantitative analysis, for example, from an XRF. And for my other classes in process mineralogy, we do the same for silicate minerals and so on, but I don't think we need that one here for mineral processing. So I'll just probably leave it here. Okay, so any examples? Sorry, any questions? Anyone with a question?
I have a question.
Yes, please come closer.
Is there a difference between minor elements and trace elements?
So trace mineral is usually very smaller in amount compared to minor minerals. But usually we refer to them for elements. So when you say trace elements, usually very difficult to quantify unless you use an equipment with very high sensitivity or low detection limit, such as secondary ion mass spectrometry can give you very detailed investigation of quantitative information. When I say minor element, it may be found in reasonable amount and can be easily quantified using a regular analytical equipment. Does that make sense? Okay, any other question? Okay, so the other thing I would like to do is probably when we go forward, I would like to make the delivery a little bit different. So I will probably talk for an hour, like a lecture slide, a lecture type presentation, and I would like to run the remaining half as a tutorial where we do some exercises. I don't know how we're going to do it, but hopefully when we do the second part on tutorials and exercises and problem solving type, you can probably involve a little bit more. You can probably ask a little bit more questions more frequently as well. So for most of the topics that we're going to cover, we'll have both lecture type and tutorial-based problem solving going forward. But this couple of weeks, I just wanted to introduce the topic a little bit, talk more about mineralogy and why it is important in mineral processing. Because if we have very poor understanding of mineralogy, then usually mineral processing doesn't make much sense. Okay, so ideally, you want to teach process mineralogy first, and then you want to teach mineral processing after that. Okay, but I will mention every now and then process mineralogy, the importance of mineralogy, and so on, so that we can couple that with processing, and hopefully that will help your understanding a little bit better. But having said that, I think you guys can give me feedback in terms of how you want to do it. I don't know why, how you're familiar back home. Maybe it's more lecture type, more discussion type, more problem solving. I don't know what is suitable for you guys. So you can probably leave comments, or you can give feedback now, whenever you want. Okay, the other thing is I have your lab manual ready, but we'll probably have to discuss a little bit with someone at your institute to see if we can do all the labs. If we can do all the labs, then that's good. Otherwise, we'll find some way to complete some of the labs, but hopefully, I know we have a few equipment there, so that may not be a problem for the labs, but we'll see how we go. So as I said last week, we'll have about 4 practicals every now and then during the semester. So hopefully that will give you more hands-on experience and learn a bit more practical things about the course as well. Okay. No question. Is anyone asking? I can't see from the back. I don't know if someone is raising their hand or they're just moving their laptop. I don't know what's going on. All good?
Yes.
All good? Okay. Thank you very much. I will. So how do you want to share the recording? Do you want me to send it to you, or because I have recorded some of today's session?
Yes.
You can share us via the Telegram.
Okay, I will try that. Hopefully it's not too big. Okay, no worries. So do you want me to send you, Elias, the slides like last week?
Yes.
Okay, no problem. Okay, thank you very much, guys. Thanks for joining.
Thank you.